Hello students. In this problem we're going to compute the curl of this vector field. Now what we have here is a vector field. We know it's a vector field because if we put in numbers for x, y, and z, the output will be a vector. I've written it in the two types of notation with the I, J, K basis vectors, or as a vector with angle bracket notation, and this is the I component, the J component, and the K component. All right, let's compute this curl. Now, the curl is denoted curl of f, which is also the nabla operator, which is the gradient operator, cross with the vector field f. And the mnemonic for that is to take the determinant of this expression here. So we put the ijk in the top component of the, or top row of the determinant, the gradient operator, ddx, ddy, and ddz in the second row of the determinants, and then in the last row we put in the vector field, the components of the vector field. And then we just simply compute the determinant. That's a way to compute the curl of this vector field. So let's go ahead and execute that determinant. So remember when we compute a determinant, I'm going to expand along the top row. So that means I'll put in an I, a minus j, because this is the first row, second column. Those components 1 plus 2, those entries add to an odd number, so we get a negative sign here, and then plus k. If you need to review determinants, that's how you actually compute determinants. The signage goes plus, minus, minus, it alternates, minus and pluses. Anyhow, that's getting a little bit far afield from what we want to do here. So just take it as I minus j plus k. Now in here we're going to compute little subdeterminants. Those are called minors. They look like this. So in this first component we're going to take this derivative from dy of y plus z and dz of e to dx. So it's everything that is not in the I column. And similarly, when we compute along the j column, we're going to take the derivative of ddx of y plus z and ddz of xy. And then similarly for k, along the k column, we will focus on ddx of e to dx minus ddy of x times y. So the determinants look like this. It's everything but the I row and the top column, everything but the j row and the top column, and everything but the k row. I'm sorry, everything but the I column and the top row, everything but the j column and the top row, and everything but the k column and the top row. I apologize for that. And now we're going to compute those determinants by applying the ddy operator to y plus z minus the ddz operator to e to dx, and similarly for the following two determinants. And when you do that, of course, the derivative with respect to y will give us a 1. The derivative of e to dx with respect to z will give us a 0. So in the I component, we're just going to get a 1. And the j component, ddx of y plus z, well, there's no x variable there, so that will vanish and we'll get a 0. And ddz of xy will, once again, give us a 0. So the j component is going to vanish. And then finally, ddx of e to dx is e to dx. That's one of those special functions that you get the function back again. And then ddy of xy, well, we take the derivative with respect to y and we get 1, and x is treated as a constant, so we just get an x there. So if we reduce that, we get I plus e to dx minus xk. And if you wanted to write that in bracket notation, you would have the following result. So it would be a 1, 0 in the j component, and then the third component. So that's the mechanics for computing the curl. In another video, I'll give some physical interpretation of the curl, the divergence, and the gradient. But for now, that's just the mechanics for computing the curl. Good luck.